Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, TIFR, Jest, IIT-Jam and other exams related to physical science. Okay, so this is the lecture number 2 of nuclear physics. Okay, and in the first lecture I have already first lecture was taken by me yesterday. Okay, so this is the second lecture, and in this lecture your nuclear physics is going to be completed, and this is the detailed course of nuclear physics. Okay, and also guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help uh, help the students to crack their exams related to physical science. Okay, and also guys, please share my lecture details to your friends so that they will also be able to watch my free live lectures and will be benefited from it. Okay, so let's get started. So in last lecture I was discussing this radioactive series, right? And the class was ended, so I'm going to start from there. Okay guys, so this is radioactive series. Okay, radioactive series, radioactive series. Okay, so at parent nuclei, parent nuclei will make daughter nuclei. Nuclei, and then it will make sub daughter nuclei, sub sub daughter nuclei. Okay, then it will make stable and product. Okay, stable and product. Okay, so this is called radioactive series, guys. Okay, so the parent nuclei will form daughter nuclei, and daughter nuclei will form sub daughter nuclei, and then stable product. Okay, this chain will continue. Okay, so here this one, for example, A1 goes to A2, and A2 become forms A3, and A3 produces A4, and so on AN. Okay, and lambda 1, lambda 2, lambda 3, and so on are the these are the radioactive constant. Okay, a decay constant. Okay, this AN, and here guys, you need to understand this is lambda 1 is greater than lambda 2, the decay constant, and lambda 2 is greater than lambda 3, and so on. Very important. Okay, so now the series I'm going to write there. I'll make a table now. Mass number. Okay, and this is series parent nuclei, and then stable and product, stable and product, stable and product. Okay. Meanwhile, just let me check whether I'm audible or not, then I'll proceed further. daughter nuclei and daughter. I'm audible, so I'll proceed further. Okay. So here there is first 4n. 4n is series. This is thorium. Thorium is denoted by Th, thorium, and then okay, series. This is thorium 90 232 thorium. Okay, and it decays and makes stable product, and that is 208 lead. Okay, 82 lead 20 or 208. Okay, so this is series. This is called 4n series. Okay, 4n. Now second is 4n plus 1 series. This is 4n series, and in 4n series this thorium is a parent nuclei, radioactive element, and it decays, and the final product becomes this one, 208 lead 82 208. Okay, now neptunium, that is Np, is denoted by Np. Neptunium, okay, Np. This is 93 237. Okay, and the product is, after decay, bismuth 83 206. Okay, this is 4n plus series. Next is 4n plus 2 series. 4n plus 2 series, that is uranium. Uranium, that is U92 U238, and the stable product is lead 206 lead Pb. Okay, this is neptunium Np. And next is 4n plus 3 series, that is actinium, denoted by Ac, and that is 4n plus 2 is actinium, guys. This is 92 235. Okay, so this is uranium 92 235 235, and this is 208 lead Pb. Okay, so here is the chart. Okay, so this is thorium, guys. This is Np. This is uranium, and this is actinium, guys. Okay, and the series is, this is 4n plus, this is 4n, this is 4n plus 1, this is 4n plus 2, and this is 4n plus 3. Okay, so this one. So this is very important series. This is 4n series, this is 4n plus 1 series, this is 4n plus 2, this is 4n plus 3 series. This is thorium, neptunium, uranium, and actinium. Okay, and stable product from these parents nuclei are that lead, bismuth, lead, and lead. Okay, so this is very important series. You can right? This is thorium, neptunium, uranium, and actinium. So you can write this like this. Okay, so by trick you can say TNUA, TNUA. Okay, this is TNUA. You can say Tanwa, right? A trick. This is trick, right? Okay. So you can memorize this word Tanwa or TNUA. So T stands for thorium, N for neptunium, U for uranium, and A for actinium. Okay, so by this you can remember this series. Okay, so this is thorium 4n series, then 4n plus 1 neptunium, then uranium 4n plus 2, and then 4n plus 3, that is actinium. Okay, and these are the stable product: lead, bismuth, lead. Okay, so this is the radioactive series, guys. Okay, next is radioactive equilibrium. Okay, radioactive equilibrium. This is also very important, guys. Okay, radioactive equilibrium. So I'll show you one radioactive reaction. Okay, this is the parent nuclei A1. Okay, this decays into A2. Okay, and then this decays into A3. Okay, and this lambda 1 is decay constant for first decay, and lambda 2 is decay constant for second decay. Okay, so suppose the number of nuclei for the parent nuclei is Ni and not. Okay, and then after decay the number of active nuclei remain is N2. Okay, and here number of active nuclei remain N3 after decay of this A2. Okay, N3. Okay, these are the initial number of nuclei for the parent nuclei. Okay, so these are the number of nuclei for these three radioactive substance. Okay, so this is the radioactive substance 1, and then this decays into this, and this decays into this. This is the stable product. Okay, so now you need to understand here that production rate, this production rate of A2, the production of rate of A2 will be equal to disintegration rate of A1. Okay, so this implies production that at radioactive equilibrium. Okay, production rate of A2, production rate of A2 will be equal to disintegration rate of A1, equal to disintegration rate of A1. Okay, so production rate of A2 is going to be equal to disintegration rate of A1. Okay, and that is going to be equal to lambda 1 N1 or N naught. Okay, lambda 1 N naught, or we can say this N1. Okay, this is N1. So lambda naught N1, lambda 1 N1. So this will, the production rate of A2 will be equal to disintegration rate of A1. Okay, its disintegration will be equal to its production. Okay, and that will be equal to lambda 1 N1. Similarly, if we talk about this reaction, so production rate of A2, production rate of A3, very important. Okay, production rate of A3 will be equal to disintegration rate of Okay, so production rate of A3 is going to be equal to disintegration rate of the production rate of A3 is going to be equal to disintegration rate of A2, and that will be equal to lambda n2 lambda 2, right? Lambda 2 n2 lambda 2 n2. Lambda 2 n2. Okay, this is the radioactive equilibrium. Okay, so so from here you can we can see this means from 1 and 2 you can say this is 1 and this is 2. Lambda 1 n1 is going to be equal to lambda 2 n2. Okay, so lambda 1 n1 equal to lambda so this is called radioactive equilibrium. Radioactive equilibrium. Okay, okay, so lambda lambda 1 n1 equal to lambda 2 n2, that is radioactive equilibrium. Okay, so very important, if this is the reaction, the production of A2 is going to be equal to disintegration of A1, and similarly the production of A3 is going to be equal to disintegration of A2, and this value is going to be production of A2 equal to disintegration rate of A1 is going to be lambda 1 n1. Similarly, this value is going to be lambda 2 n2. So for radioactive equilibrium, if it is radioactive equilibrium or in radioactive equilibrium, lambda 1 n1 will be equal to lambda 2 n2. Okay, lambda 1 lambda 2 are decay constant or decay rate. Okay, so this is radioactive equilibrium. Well, so I'll give one example. Suppose we have 10 nuclei, okay, and 5 got decayed, 5 decayed, okay. We have 10 nuclei, 5 decayed, and 5 remained, right? And then 3 that this one 3 got decayed, 3 got decayed, then 2 will be removed, right? This one. So 5 decayed, right? Here 5 decayed and 5 remained. Here 3 decayed, 2 remained. Okay. Well, so for example, here also they like, if you take this A1, this is A2, and this is A3. So in this case, that lambda n1 will be equal to lambda n2 for radioactive equilibrium. Okay, or we can take one more example, that is there are 2 nuclei, radioactive nuclei, and there are also 2 radioactive nuclei, and there are 2 radioactive nuclei. This is A1, A2, A3. Okay, 2 got decayed, so we've got 2 here, right? 2 got decayed, the production is 2. 2 got decayed, then production is 2. Similarly, 5 got decayed, right? Production is 5, and 3 got decayed, production is 2. Okay, this is 2 got decayed. Similarly, you can see 2 got decayed means 2 got decayed, production of 2 here. 2 got decayed, production of 2. Okay, so this is the case of radioactive equilibrium. Okay, well, now I'm going to solve a very important question. Okay, before that you need to note down one more thing, very important thing, and that is lambda effective, guys. Okay, lambda effective. Lambda effective is equal to lambda 1 plus lambda effective equal to lambda 1 plus lambda 2. For example, for like this, we have X nuclei, right? It gets decayed into Y and Z, and the decay constant for this is lambda 1 and this is for lambda 2. Okay, right? In this case, lambda effective is going to be lambda 1 plus lambda 2, okay, because this is going to, this x is decayed into two elements, right, y and z, and decay constant is lambda 1 lambda 2 for these two. So lambda effective is going to be lambda 1 plus lambda 2. Important thing, guys. Okay, okay, and so in that case the n is going to be, I have already explained it, n is going to be n naught e to the power minus lambda t, right? So here e to the power minus lambda 1 plus lambda 2 t, or we can write n equal to n naught e to the power minus lambda effective t. Okay, this is lambda effective t. These are important formulas, guys. Now I will solve one question. Okay, it will clear your all doubts. So question is very important question. Uh, so we have x that is decayed into y and z. Okay, we have x in and it is decayed into x and y, and we have been given tm1. Okay, so tm1 is given, that is 1620 years, mean average life. Okay, mean time life, mean time life, and tm2 is given, for this tm2 is given, that is equal to 405 years. Okay, so this is the reaction we have been given for this. For x to y, the mean lifetime is given, that is 1620 years, and for x to z the mean lifetime is given, tm2 405 years. Okay, and now what we have to find, that find out the time, find out the time when 1/4 of initial 1/4 of initial nuclei 1/4 of initial nuclei 1/4 of initial nuclei remain active, remain active. Okay, so options are, option A is 420 years, option B is 449 years, option C is 342 years, and option D is 2 years. Why is years? Okay, this is the question, guys. So question is, so we have given a reaction, right? So x decays into y and z. For y to x decays, for x to y, we have been given mean lifetime, that is 1620 years. For z, x to z, mean lifetime is given. Now what we need to find out the time when 1/4 of initial nuclei remain active. Okay, so when 1/4 of initial nuclei remain active. Okay, so so we can say, very easy one, guys. So this is a simultaneous decay case. Okay, this is the case of simultaneous decay. So simultaneously it is decaying into two elements, right? So it is called simultaneous decay. For suppose this is lambda 1. Okay, for decay constant is lambda 1 and this is lambda 2. Okay, so in that case, so this is a case of simultaneous decay. Okay, it is the case of simultaneous decay. Is the case of simultaneous decay. So it means lambda effective will be lambda 1 plus lambda 2. Okay, so in that case n is going to be, we have a formula, right? N equal to n naught e to the power minus lambda t. So here it is going to be, in this case it is going to be e to the power minus lambda effective t, right? Because it's a case of simultaneous decay. Okay, so here now it is going to be this one, or we can solve it first. So lambda effective. Okay, so question is asking, so we need to find out the we need to find out the time when 1/4 of initial nuclei remain active. 1/4 of initial nuclei remain active means n naught by 4 is going to be equal to n naught e to the power minus lambda effective t, right? Lambda effective t. So n naught will get cancelled, and so this implies e to the power this one, or we can write 1 by 4. 1 by 4 is going to be equal to e to the power minus lambda effective t. So from here this is going to be e to the power lambda effective t is going to be 4 by log property, right? Just a property. So what we have done, this e to the power lambda effective 1 minus e to the power minus lambda effective t is going to be equal to 1 upon e to the power lambda effective t. So we'll cross multiply, so we've got this guy, right? So from here so lambda effective t is going to be ln 4, right? ln 4, and from here t is going to be equal to ln 4 upon lambda effective. Lambda effective value, we know that lambda 4 equal to lambda 1 plus lambda 4. Okay, now here we know, since we know tm mean lifetime is equal to 1 upon lambda. This is I have already explained. So decay rate, the mean lifetime is equal to 1 upon lambda. Lambda is decay rate, right? So from here this implies lambda 1 is going to be, or we can write lambda is going to be 1 upon tm, right? Mean lifetime. So from here we can get lambda 1 is going to be 1 upon tm1. So that is 1 upon tm1 is given, that is 1620, right? 1620, and lambda 2 is given 1 upon tm2. This is given in the question, so that is 1 upon 409. Oh, sorry, 405. So we'll put the value. So therefore this implies t equal to, we'll put value here, right? Suppose this is equation 1. So this is going to be ln 4 upon 1 upon 1620 plus 1 upon 405, lambda 1 upon lambda 2, right? These are the values. Now we'll solve it simply. So this is very simple. We can calculate it, and this value is going to be simple one, ln 4 upon this one. This is 4 plus 5, or this is, will take LCM, that is 1620, and this is going to be 1 plus 4. Okay, so if we solve it, so this value is going to be this value is going to be this one, or this we can write ln 4, we can write 2 ln 2, right? So this value, if you solve it, so this value is going to be very simple. So you can put the value, log 2 value is 0.693, right? So if you put the value, so you are going to get almost 449. So this t value is going to be 449 years. 449 years. Okay, so this is the answer. So which option is matching, guys? Let me check which option is matching. 449 years. 449 years. Option B is the correct option. Okay. Next question, guys. There's a point I'm going to write. So this is the question which is asked in CSIR net. Okay. I'm writing it as a statement. Okay. I would suggest you please note down and memorize it, because the solution of this question is very lengthy, right? But I will solve that question in my PYQ session. Okay. Here you need to note down as a statement. It's a very good question. So it is asked in CSIR net. Okay, so statement is, so we have been given a reaction. Okay, so this is given x decays into y and y decays into z. Okay, and this is the lambda 1 and this is lambda 2. These are decay rate. Okay, and the number of nuclei initially for this parent nuclei is n0, and for this remaining active nuclei is n1, and this is, or this we can write, this is suppose n2 and this is n3. Okay, this one. So for that, what we need to find, so this is the decay equation. Okay, x decays into y, y decays into y, z. Okay, so what we need to find, we need to find the number of nuclei of z at time t. Okay, so this is the equation. So we need to find n0 is initial quantity of x. Okay, initial quantity of x. So here n0 is initial quantity of n0, where n0 equal to initial quantity of x. n0 is initial quantity of x. Okay, so I'll write a statement. Okay, so that implies number of nuclei of z. Okay, so number of nuclei of z at time t. Okay, so n naught is, or n0 is the number of nuclei of x. Okay, so number of nuclei of z at time t, that is the number of nuclei of z at time t, that is n3, is going to be equal to lambda 1 lambda 2, the product of decay rate, into n naught, the initial quantity of this parent nuclei, into t naught by 2, t naught into t square by 2. Okay, so t square by 2, t square by 2. This is very important result. So you should note down and memorize it. I will solve this question also. Okay, in my PYQ session I'm going to solve it. It's a lengthy question, but I will solve it. Okay, so n3. So if this is the reaction we have been given, and these are the decay constant which are given, right? And suppose the initial number of nuclei are n0 of this parent nuclei. So we have to find, if we have to find the number of nuclei, number of active nuclei of z, so that value is going to be, n3 is going to be equal to lambda 1 lambda 2 into n naught t square by 2. Okay, at time. So this is important result. You need to note down and memorize that. Okay, well, this is n3 equal to lambda 1 lambda 2 and not t square by 2. Okay, important, and asked in CSIR net. Next question guys. Next is Next, we are going to study stability of nucleus. Okay, stability, stability of nucleus, of stability of nucleus. So I'll draw the graph for it. Stability of nucleus. When nucleus is, what are the condition for nucleus being stable? Okay, so if you draw the graph between if you draw the graph between Z and N, between Z and N, okay, so this is a graph between Z and N. So we'll get this one graph, okay, this one. Okay, these are straight line, and this is NZ, N by Z, N by Z, and this is N by Z. Okay, this is N by Z. So N by Z is 1, and this is N by Z equal to 1. So this is the zone of stability. Zone of zone of stability. Zone of stability. Okay. So if the ratio of nz, okay, ratio of n upon z, or n by z value is between 1 to 1.3, right? Right, for any nucleus, if the ratio of n and z is between 1 to 1.3, then that nucleus is stable nucleus, guys. Okay, so for stability, for stability, for stability, for any nucleus, n by z should be, the value of n by z should be between 1 and 1.3. Very important one. Okay, so this is the stability region of the nucleus. So stability, so if the ratio of nz is between 1 to 1.3, then that nucleus is a stable nucleus, guys. Okay, so and this is the and graphically we can represent like this. Okay, so this is the graph between n and z, and the so this region, n by z equal to 1, n by z equal to 1.3. So this region, dotted region, is the stable region. Okay, zone of stability. So for any nucleus to be stable, the nz value, their nz value, right, should be between n is number of nucleon. Okay, the ratio of number of nucleon and the atomic number must be between 1 to 1.3. I hope you have understood it. Next point. Okay, next point is binding energy curve. Very important, guys. Okay, you will be asked question in interview as well. Binding energy curve. Okay, so BE curve in short, we'll write BE curve, BE curve. Okay, or binding energy curve. Binding energy curve. Okay, so binding is, so this is the curve between binding energy per nucleon, binding energy per nucleon versus atomic mass number. Okay, atomic mass number. Okay, so binding energy curve is binding energy per nucleon versus, the binding energy curve is between binding energy per nucleon versus atomic mass number. Okay, so I'll make up this curve. This one. this is the curve, guys. This is binding energy per nucleon versus atomic mass number. Okay, this is the curve. This is the binding energy curve, and this is this value. This is binding energy curve. Okay, this is for proton 1h2 deuterium. Okay, 1h2, the binding energy per nucleon is 1.1 MeV. 1.1 MeV. Okay, this is helium, this is carbon, this is oxygen. Okay, and this is going to be like this. Okay, this is, guys, 8.8 MeV. Okay, this is 8.8 MeV. This is the binding energy per nucleon. Okay, and this is, guys, so this is okay. So this is F for Fe. This is for Fe. Okay, this one. This is the curve. Okay, this is the curve, and for this is Fe for 56. Okay, Fe 56. The atomic mass is 56. Okay, okay, and this is binding energy per nucleon, and this is Fe. Okay, and this is the binding energy. So highest, the binding energy per nucleon is highest for Fe. Okay, this one, and whose atomic mass is 56. Okay, this is the binding energy curve. Okay, guys, now I'll explain this curve. Okay, first is the minimum binding energy per nucleon is for deuterium, is for deuteron. The minimum binding energy is for deuteron is 1.1 MeV. The minimum binding energy is for deuteron is 1.1 MeV. Okay. Okay, so we can see here. So this is deuteron. So minimum binding energy is for deuteron. Okay, that is 1.1 MeV. Next point. Next point is binding energy curve, BE curve, is continuous. Curve is continuous BE curve is continuous except BE curve is continuous except some finite peaks at 2He4, 4Be8, 6 carbon 12 and 8 oxygen 16. Okay, so binding energy curve is continuous except some finite peaks. Okay, so these are some finite peaks. Okay, this is for helium, carbon, oxygen, and there is for beryllium as well. Okay, there are more peaks. Okay, I have shown 3 only. So you can see this is a binding energy curve. So this is continuous except some finite peaks. Okay, if it accept these these peaks, right? So this curve is continuous. Okay, very important curve because in interview you can be asked to explain binding energy curve. Okay, for PhD interview. Next is binding energy is maximum for Fe, right? This one you can see binding energy, that is 8.8 MeV, the maximum for Fe. For others it is less than that. Okay, so you can write Be is minimum, sorry, is maximum for Fe. Okay, implies that is 8.8 MeV. Okay, so you can see Be is maximum, binding energy per nucleon is maximum for Fe. Okay, next, most stable nucleus. Okay, so because this is binding energy, so the binding energy is maximum for Fe, it means the binding energy per nucleon is maximum for Fe. It means Fe is the most stable element. Okay, nucleus. So implies most stable nucleus is Fe. So Fe is the most stable nucleus, guys. Okay, because the binding energy per nucleon is maximum. More the binding energy per nucleon means more the nucleus will be that more the nucleus will be stable. Okay, so binding energy per nucleon for Fe, that is 8.8 MeV. You can see in the figure. Okay, next is so this is the binding energy per nucleon. If you get the just binding energy for Fe, then this is going to be 8.88 into 56, and that is going to be 492.8 MeV. This is binding energy. Okay, so binding energy is different and binding energy per nucleon is different. Okay, and similarly binding energy for bismuth, if it get Bi, so that is going to be 8.8 into bismuth is directly I'll write, that is 1640 MeV, that is 1640 MeV. Okay, now binding energy per nucleon for bismuth is that is 1640 upon 209. Okay, so atomic mass of bismuth is 209, so that is 7.8 MeV. Okay, so we can write the binding energy Be per nucleon is maximum for stability. Binding energy is maximum for stability. So for any element, if you have to check the stability, so we'll check the binding energy. Okay, if binding energy is maximum, then that element is stable. Okay, more stable. So binding energy is maximum for stability. Binding energy per nucleon is maximum for stability. Okay, not only the binding energy. Okay, so by checking binding energy, we cannot tell that atom, that element is stable or not. We'll check binding energy per nucleon. Okay, next is, if heavy nucleus breaks into, if a heavy nucleus if a heavy nucleus if a heavy nucleus breaks into heavy nucleus breaks into small nuclei, then binding energy per nucleon, BAE, right, increases to achieve stability. Okay, so if heavy nucleus, that is heavy radioactive nucleus, breaks into small nuclei, then binding energy increases, because every nucleus want to be stable, right? So for that they break, they disintegrate, right? So for heavy nucleus, if heavy nucleus breaks into small nuclei, then binding will, because they will be more stable, right? Means the binding energy increases to achieve stability. Okay, next point is, if a small nuclei, if if a small nuclei if a small nuclei bind into heavy nucleus, heavy nuclei if a small nuclei bind into heavy nuclei, then also binding energy per nucleon increases to achieve stability. Very important. Okay, stability. Okay, so if a small nuclei bind into heavy nuclei, okay, or heavy nucleus, then also binding energy increases to achieve stability. Okay, so for getting stability, small nuclei can also bind together and make a heavy nuclei. Okay, so this is about binding energy curve. Okay, very important. So especially you will be asked in interview. Okay, also in the examination. Okay, this is the one. Next is liquid drop model, guys. It is also important. Liquid drop model. I'll solve questions also. Okay, liquid drop model. Liquid drop model. Liquid drop model. Okay, for nucleus. Okay, liquid drop model. So first point is incompressible. means nucleus is incompressible. Okay. Nucleus and liquid drop both both are incompressible. Okay, both are incompressible. Okay. Nucleus and liquid drop both are incompressible. Okay, next is density. So we have given this liquid drop model because this nucleus has similar properties like liquid drop. Okay, second is density. Density rho is going to be equal to, that I have explained, that is rho naught, which is constant. Okay, rho naught, which is constant, rho equal to rho naught. Okay, when r less equal to r, and this is equal to 0 when r greater equal to r. Rho is constant, guys. Okay, this is the density of nucleus. Third is nuclear forces. So in nucleus there are nuclear forces, right, which are short ranges. Okay, nuclear forces which are short range forces in nucleus. Short range forces. So nuclear forces, that is short range forces. Okay. And if we talk about so there are nuclear forces or short range forces. If we talk about liquid, okay, so then there is van der Waals forces, that is also short range forces. Okay, and in case of liquid there is van der Waals forces. Okay, this is also short range forces in case of liquid. Short range forces. Okay, in case of liquid. Okay, liquid drop. So van der Waals forces are short range forces. Similarly, if you talk about nucleus, so there are nuclear forces which are short range forces. Fourth point is nearest neighbor interaction. Okay, so nearest neighbor interaction. Okay, so they have saturation property. Okay, because they interact with nearest neighbors. Okay, and then this gets saturated. So saturation property for a nucleus. Okay, saturation property. Okay, or in case of liquid drop, they have surface tension. Okay, liquid drop, they have surface tension. they have surface tension. Okay, next is fifth point. To break a nucleus into its constituent particle, to break a nucleus, to break a nucleus into its constituent particles, into its constituents particle, to break a nucleus into its constant particles in case of nucleus. Okay, binding energy is required, right? Binding energy, I'm writing it short, binding, BE, binding energy is required. So to break a nucleus into its constant particles, binding energy is required. And in case of liquid, to break liquid drop, to break the bonding in liquid to break the bonding in liquid drop, latent heat is required. Latent heat is required. Latent heat is required. Okay, so to break the nucleus into its constant particles, binding energy is required for in case of nucleus, right? And if you talk about this liquid drop, for breaking the bonding in liquid drop, latent heat is required. Okay, so they have they both liquid drop and nucleus have similarity. Okay, okay, next is volume energy. Volume energy in liquid drop. Okay, volume energy in nucleus. Volume energy, that is EV, is proportional to A, that is atomic mass. Okay, or we can write this one, EV is proportional to this one, A is this one, 4 by 3 pi r cube, 4 by 3 pi r cube, since r is equal to r naught e to the power 1 by 2. Okay, this we know, right? R is r naught e to the power 1 by 2, and r is radius of nucleus. Radius of nucleus. Okay, radius of nucleus. So EV is proportional to, so we can write R is proportional to, my apologies, EV is proportional to R naught e to the power 1 by 3 r cube. That implies EV, the volume energy, is proportional to this one. R value is this, right? A. EV is proportional to A. Next is surface energy. Surface energy surface energy surface energy. Okay, so surface energy, that is denoted by Es, is proportional to 4 pi r square, right? Surface is proportional to 4 pi r. The surface energy is proportional to 4 pi r square. So since we know r is r naught a to the power 1 by 3, right? So Es is going to be proportional to e to the power 2 by 3, right? Third is Coulomb energy. Okay, COULOMBS, Coulomb's energy. Coulomb's energy. So that is proton Coulomb energy, or proton repulsion. Okay, or we can say PP repulsion, proton repulsion. Coulomb energy is because of protons in nucleus, right? So we know U, potential energy, is equal to K Q1 Q2 upon R. Q1 Q2 upon R, right? Force is K Q1 Q2 upon R square, right? Use this. So EC, in this case of this, EC value is 1 upon 4 pi epsilon 0, 1 upon 4 pi epsilon 0 E square into Z minus 1 upon R into 2. Okay, R into 2. So from here, this is important one, EC, that Coulomb energy, EC, Coulomb energy, is going to be proportional to, or Coulomb energy is equal to AC Z into Z minus 1 upon a to the power minus, a to the power 1 by 3, a to the power 1 by 3. Okay, so EC is going to be equal to minus AC Z into Z minus 1 upon a to the power 1 by 3. Okay, here minus sign, shows the decrease in binding energy. Okay, so decrease in binding energy. Minus sign implies decrease in binding energy. Okay, next is fourth. This is third, right? Fourth is asymmetric energy. Asymmetric energy. Asymmetric energy. Right? So here asymmetric energy, in the case of asymmetric energy, EAS is proportional to N minus Z whole square upon A. Or we can write EAS is equal to minus AAS, right, asymmetric constant, into A minus 2Z, A minus 2Z, N minus Z, right, and equal to A plus Z, right. So A minus 2Z, A minus 2Z whole square upon, this is the asymmetric energy. Okay, this one. Next, last is pairing energy. Pairing energy. Pairing energy, that is EP. EP is equal to plus AP upon a to the power 3 by 4. This is for even, okay, and EP, that pairing energy, that is equal to minus AP upon a to the power 3 by 4 for odd. These are the different energies, okay. There's asymmetric energy, surface energy, Coulomb energy, volume energies, okay, the unpairing energy. Next is semi-empirical formula. I'm going to write now. So that is binding energy. Using those different energy, the binding energy of nucleus is going to be AVA. This is surface energy, volume energy, AVA. Then AS, surface energy, a to the power 2 by 3 minus AC Z into Z minus 1, AC Z into Z minus 1 upon a to the power 1 by 3 minus AC Z into Z minus 1 upon a to the power 1 by 3 minus AS, AAS, that is asymmetric energy, very important formula, okay. AAS, asymmetric energy, is A minus 2Z whole square upon A. 2Z whole square upon A plus minus AP upon a to the power 3 by 4. This is the binding energy and very important formula, okay. This is called semi-empirical formula, okay, for nucleus, binding energy for nucleus, okay. So this is very simple. The B is equal to AVA. You can note down and memorize it. This is B equal to binding energy equal to AVA minus AS a to the power 2 by 3 minus AC Z into Z minus 1 upon a to the power 1 by 3 minus AAS A minus 2Z whole square upon A plus minus AP a to the power 3 by 4, okay. So this is binding energy and this is called semi-empirical formula, okay. B. Next, if you based on this formula, you will be asked many questions. So I have seen many questions asked, right, for related to this formula, okay. So now you need to know this. This is the B, okay. So for most stable, isobar del B is a binding energy, okay. Del B upon del Z equal to 0. Very important. B is binding energy, okay. So if you have been given this formula, right, and you need to find out the most stable isobar, okay. So you have to differentiate it with respect to Z, okay, and B is binding energy here, okay, binding energy. I will solve question, then it will clear your doubt, okay. Energy, binding energy, okay. So del B upon del Z equal to 0, okay. For most stable isobar, del B, that binding energy, B is binding energy, okay. So if you have given binding energy and if you have and we have been asked the find out the most stable Z value of most stable isobar, so what we are going to do, we are going to differentiate that binding energy with respect to Z and we'll put that equal to 0 and we'll get the value of Z, okay. So now I'm going to solve question, and here you need to know this. I'll write in the question, okay, very important thing. So question is asked in okay, question is asked in CSIR net, CSIR net, CSIR net, CSIR net 2020. Okay, CSIR net 2020. So we have been given B value. Okay, binding energy is given A1A minus A2 A to the power 2 by 3 minus A3 Z square A to the power minus 1 by 3. Okay, and then minus A4 A minus 2Z whole square A inverse. Okay, this is the binding energy we have been given, right? So before that, you need to note down one. So for that, so we need to find out the value of Z for most stable isobar. Okay, value of Z for value of Z for value of Z for most stable isobar. Okay, so this is the question. So we have been given binding energy. This question is asked in CSIR net 2020. Okay, this question paper I have already solved, so you can check this question in my playlist. Okay, so this is so we have been given binding energy and we need to find out the value of Z for most stable isobar. Okay, so procedure is simple. I have already explained. So for most stable isobar, for most stable isobar, what we are going to do is del B upon del Z equal to 0. dB upon dz equal to 0. That's what we have to do. dV over dz equal to 0. So what we need to do, we have been given binding energy, we have to differentiate this with respect to Z, and then we'll find the value of Z for most stable isobar. Okay, so what we'll do is we'll just differentiate this with respect to Z and we'll get the answer. Okay, for most stable isobar. So we need to find value of Z for most stable isobar. Okay, so for most stable isobar, del B upon del Z, will put del B upon del Z equal to 0, means we'll differentiate binding energy with respect to Z and we'll put that equal to 0 and we'll find the value of Z for most stable isobar. This is the procedure, guys. And we can simplify this procedure. So there is a so we can simplify this procedure. Okay, we can make our calculation easy and shorter by so by these two formula, guys. You need to note down. Okay, so and that formula we have got by differentiating this with respect to Z. Okay, so I'm going to write directly because you need to note down and memorize it, guys, because if you know those formulas, so you can quickly solve questions in the examination. Okay, so that is, the first is value of Z equal to that is, you just need to write A upon 2 plus AC upon 2AA, that is asymmetric energy. Okay, 2AA into A to the power 2 by 3. Very important formula. The second is, by calculating this, second is Z equal to A upon 2 plus 0 2 plus 0.015 A, 0.015 A to the power 2 by 3. Okay, these two formula you need to note down, guys. Very important formula. Okay, if you know this formula, you don't need to differentiate it and then calculate it. You can directly get the answer. Okay, These are very important formulas. So Z equal to A upon this formula, Z equal to A upon 2 plus AC upon 2AA into e to the power 2 by 3, or Z equal to A upon 2 plus 1.015 e to the power 2 by 3. This is by calculating this constant, okay, this formula. So now by this formula I can easily solve this question, okay. So for most stable isobar you need to find the value of Z, right? So I directly use this formula. So so Z is going to be this formula, this is Z is going to be this one. And here guys, in this question it is also given, it is given A4 upon A3 is given, A4 upon A3 is given, that is almost equal to 30, okay. So I am going to use this formula. So this is Z equal to A upon 2 plus AC upon 2AA e to the power 2 by 3, okay. So Z value is going to be, so directly I'm not differentiating it with respect to Z and putting it equal to 0. Directly I know this formula, so I'm just putting it. These two formula are very important guys, you need to note down and memorize it, okay. Practice solving and solve many questions using this formula, then these formula are automatically going to be in your fingertips, okay. Okay, so Z is going to be A upon 2, that here you need to understand guys, A1 is volume energy, volume coefficient, okay. This is surface coefficient, this is Coulomb coefficient, and this is asymmetric coefficient, okay. So I can write this like this, okay. So this is going to be 2 plus AC means this one, AC means A3 upon 2A4 e to the power 2 by 3, right? Or we can write A upon 2 plus A3 upon A4. We have been given A4 upon A3 equal to 30, means A3 upon A4 is 1 upon 30, right? So we can write into 1 upon 2 into 1 upon 30 into e to the power 2 by 3, okay. So then this value is going to be, so we will calculate it. So this is going to be this one, 60A upon 120 plus e to the power 2 by 3, okay. How? This is 1 by 60 a to the power 2 by 3, right? We'll take LCM, that is going to be 60. 60 will go upright and 60 to the 120, right? So this is going to be 60A. So value of Z is 60A upon 120 plus 60 Z equal to 60A upon 120 plus e to the power 2 by 3. Now you can see how quickly within a minute we have solved this question if you know this formula, right? So because in examination we need more or less, we have a limited time, right? So we need if we know the trick or if we know the formula, right? So we can solve easily, right? We can save time. So that's why the formulas are very important. You need to note down, okay. So now because you know the formula, that's why you have solved it in within a minute, right? If you don't know this formula, then it will take time, right? Okay, so you can save your time and you can solve more questions in the examination. Okay, so this is the answer guys. I hope you have understood it. Next question guys, I'm going to do. Next question is, so just guide is just give me 1 minute guys, okay, then I'll start. Okay guys, let's get started, okay. Next question I'm going to solve. Next question is the masses of H atom. The masses the masses of H atom, that is neutron, masses of H atom comma neutron and 238 uranium are given by 1.0078 comma 1.00878 and 238 238.0508 AMU, okay, atomic mass unit respectively. Okay, the binding energy of 92 uranium 238 is, okay, options are option A 120 MeV, option B 2500 MeV, option C 1800 MeV, and option D 140 MeV. Okay. So this is the question. So masses of hydrogen atom, neutron, okay, hydrogen atom means proton, okay, and neutron and uranium 238 are given, okay, and we have to find binding energy, okay. Very simple question. Since we know here binding energy B equal to delta M C square, right? Delta M is defective mass defect, right? So here delta M is going to be, that we know, right? That is ZMP, mass of proton, plus Mn, mass of neutron, minus Mnu, mass of the atomic mass of that nucleus, okay, uranium nucleus, right? This we know. So from here, this is the value, right? So binding energy is going to be, BE is going to be, this value will put delta M value, right? So this is ZMP. Z means Z is this uranium, right? 92 uranium, 238 means 92 into number, that atomic number, right? 92 into mass of proton, that is 1.0078 plus that mass of the number of neutron means 238, that is atomic mass, minus atomic number, that is proton number, neutron number, right, into 1.00087 1.00087 minus this one 238.0508, okay, this is delta M into C square, into it will convert it into that C square is going to be 931.5 upon C square, right? MeV, right? C square. CC will get cancelled and we'll solve it. Then binding energy is going to be 1800 MeV. This is the answer, guys. Which option is matching? Option C is matching. Okay, and here we know, guys, this one we have converted this into MeV. Okay, so this is the answer, guys. I hope you have understood. Very simple question, right? Just we need to know this binding energy formula, right? Delta M is ZMP minus MMN, right? This is mass of neutron minus MNU, mass of nucleus. Okay, well, next question, guys. Next question is, next question. This is asked in Jest, okay? Jest. Question is Jest 2015. Question is the stable nucleus that has 1 by 3 of the radius of 189 OS osmium OS nucleus, 189 OS nucleus, okay, is, so we need to find the stable nucleus that has 1 by 3rd of the radius of 189 OS nucleus is, okay. That we need to find. The options are the stable nucleus we need to find out that has 1/3 of radius of osmium 189 nucleus is, okay. Whose radius is 1/3 of this the radius of osmium nucleus, okay. So options are given. Option A 7, 3 Li, option B 8O16, option C 2He4, and option D 7N14. Okay, so these are the options. So since we know we have a formula that is R is proportional to A to the power 1 by 3, or so from here we can write R1 upon R2 is equal to A upon A1 upon A2 to the power 1 by 3. We can write it, right? So 1 by 3. So we can put the value of R1 and R2. Okay. So R1, because in question it is given, since R1 is R2 by 3, this is given, right? Given according to the question. So we'll put it. So this is going to be R1 upon 3 upon R2. That is going to be equal to A1 value. A1 value we have to find, right? A1 value. A1 upon this value is A2 value is given 189 to the power 1 by 3 to the power 1 by 3. Okay, so this is R2. This is R2. Okay. So R2 will get cancelled. So 1 by 3 is going to be equal to A1 to the power 1 by 3 upon 189 to the power 1 by 3. So from here we can get this one A1 value. A1 value is going to be this 189 upon 3 to the power 3, right? Because 8 to the power 1 by 3 will go this side, so 1 by 3 and 3, 1 by 3 into 3 will cancel. This will be 189, and 3 to the power 3. 3 to the power 3 is, I'm going to write directly, that is 27, right? So this value is going to be equal to 7. So atomic mass is 7. So which is the option 7? This so 7 lithium 3 is the correct answer. Option A is the correct answer, guys. Okay. So this is A1 equal to 7 means 7 Li 3 Li 7. Right? 3 Li 7. Okay. This is the answer. Just question. Next question is, asked in TIFR, guys. Okay. This is a TIFR question. TIFR 2011. Okay. This is a good question. Question is given that the ionization, the ionization energies of 1H1 and 3Li are 13.6 electron volt and 5.39 electron volt respectively. Okay. The effective nuclear charge the effective nuclear charge experienced by valence electron of 3Li 3Li atom may be estimated in the terms may be estimated in the terms of electron as. Okay, this is a question, guys. Okay, very good question. So question is, given that the ionization energies of hydrogen atom and lithium are given. Okay, so these are the ionization energy, okay, respectively. The effective nuclear charge that is Z, experienced by valence electron of lithium, okay, valence electron, the outermost electron of lithium atom, okay, may be estimated in terms of electron as, okay. So there is a formula, guys, okay. So here you need to know this is a lithium atom. This is lithium atom, this is nucleus, okay, this is nucleus, okay, this is the first cell n equal to 1, this is n equal to 2, right. So there are one electron, outermost electron 1, okay, there are two electrons, right. So the effective nuclear charge experienced by this outermost electron of lithium, that's what we need to find out. So we have a formula, guys, you need to note down. The formula is Z effective equal to simple root ionization energy of lithium into n square, that is n is the that level, okay, energy level, upon that 13.6 means the ionization energy of hydrogen, right. So Z effective is going to be Z effective, the charge, the effective nuclear charge experienced by valence electron of Li is going to be this. Z effective is going to be ionization energy of lithium is given, right, that is 5.39 into n square, the outermost electron for Li is, and for which level, that is n equal to 2 level, right. So 2 square upon 13.6, this is the potential energy of hydrogen, right. So we'll solve it. So this value is going to be 1.26 electron, 1.26 E, okay, 1.26 E, okay. So this is the answer. This is a TIFR question, guys, okay, very simple. So this is the one, okay. This formula you need to note down, guys, okay, very important formula. So effective nuclear charge experienced by lithium, Z effective is root ionization energy of lithium into n square, that is energy level upon 13.6, okay. Okay, guys, next is nuclear fission, okay? Nuclear fission, okay. So nuclear fission example is this is the X parent atom, right. So 60 this is 150 X, okay, 150 X, the atomic mass number is X, okay. So this is unstable nucleus, and this becomes 60Y plus 90Z, okay, plus delta I. So this is unstable nucleus. Unstable nucleus. Unstable nucleus, and these are stable nucleus, okay, 150 stable nucleus. So that radioactive element, okay, decayed into two stable nucleus plus energy is released, okay. So that is called, this is the nuclear fission, and the energy is delta I. This energy is 60 EY, energy of 60 into energy of EY Y plus 90 into energy of Z minus 150 into energy of X, okay. or we can write delta E, important formula, mx minus my minus mz, mx minus my minus mz into c square. Okay, this is the energy release, important formula, guys. Okay, this one. Okay, guys, next is nuclear fusion. Okay, nuclear fusion. Nuclear fusion, that is, suppose 25A plus 3B, two atoms, okay, react together and they make 28C plus delta I. Okay, so this is the fusion. Okay, this parent atom breaks into two atoms. Okay, stable atoms. Here two atoms combine and form one atom, one stable atom. Okay, this is fusion and this is fission. Okay, fusion is this delta I, and here this is a thermonuclear reaction. Okay, thermonuclear reaction, and that is between 10 to the power 6, temperature of this between 10 to the power 6 to 10 to the power 7 Kelvin. Okay, this is the nuclear fusion. Okay, next is guys, this is magnetic moment. Okay, magnetic moment. Magnetic moment. Magnetic moment. Proton and neutron both possess magnetic moment. Okay, proton and neutron both possess the magnetic moment. Both possess the magnetic moment. Okay, so here mu L is going to be equal to GL mu n upon h cut into L. Okay, so mu L equal to the magnetic moment GL. Okay, so here, and similarly mu S spin magnetic, this is orbital magnetic moment, right? This is spin angular magnetic moment, magnetic moment. This is going to be GS mu n upon h cut and S. Okay, and here mu n is a nuclear magneton, like Bohr magneton we have studied in atomic and molecular physics, right? So similarly, mu n value is E h cut upon 2mp, E h cut upon 2mp, E h cut upon 2mp. Okay, E h cut upon 2mp, and this is called nuclear magneton. Nuclear magneton. Okay, so this is nuclear magneton, guys, important one. So, and here we know that mp is almost equal to 1836 into me, right? So from here, and mu b, we know mu b, the Bohr magneton, right? This is E h cut upon 2me, or we can write instead of me this value 1836. Okay, 1836 ME, right? So this is going to be mu B is going to be E h cut upon 2 ME, right? Or we can write E h cut upon 2 into ME values from here. This is going to be 2 MP upon 1836, right? And this value is mu n, right? So this is going to be then mu B is going to be 1836. 1836, this will go up, right? 1836, this value is this one, this value is mu n, right? 1836 mu n. This is important. This is the relation between Bohr magneton and nuclear magneton. Okay, nuclear magneton. Bohr magneton is 1836 times of nuclear magneton. Okay, so mu B equal to 1836 mu n. Okay, and there is one more thing that you need to know, this one. Okay, next is that for proton mu p value is going to be that magnetic moment is going to be gp mu n upon h cut s. Okay, and for neutron mu n is going to be gn into mu n upon h cut s. Okay, so this is mu p gp mu n upon h cut s, and for mu n this is gn mu n upon h cut s. Okay, and if you get this value, these values are very important. I'm going to write. So mu p for the magnetic moment for proton is 2.79 mu n. Very important, you need to note down. Okay, mu p equal to 2.79 mu n. Okay, 2.79 mu n. This is the magnetic moment of proton. Okay, and the second is mu n, that is magnetic moment of neutron, that is equal to minus 1.91 mu n. 1.91 mu n. Okay, 1.91 mu n. This is mu p is 2.79 mu n, right? And mu n is minus 1.91 mu n. This formula, these are very important. Right? This is also important. Okay, you need to note down. Mu p equal to 2.79 mu n and mu n equal to minus 1.91 mu n. Okay, this is the one. And these two formula also you need to note down. This one, mu pz, okay, for proton, z component of magnetic moment of z component of proton, that is gp mu n ms, okay. And for neutron, that z component of neutron, that mu mz, that is gn mu n ms. Okay, so these formula are also very important. You need to note down. These are z component, and this is also very important. Okay, so this is about magnetic moment, guys. Gn. Okay, next is guys, shell model. Okay, important one. Shell model. This is important, guys. Okay, shell model. So liquid drop model, liquid drop model, couldn't explain the magic numbers, couldn't explain the magic numbers. Okay, so as in inert gases, the separation separation energy separation energy for proton separation energy for proton and neutron is high for for some particular magic numbers, high for some particular magic numbers, okay. So this is shell model. Liquid drop model couldn't explain the magic numbers. As in inert gases, the separation energy for the proton and neutron is high for some particular magic numbers, and that's why the liquid drop model is not able to explain the magic numbers. Okay, so now here I'm going with a very important thing. I'm going to write for examination purpose. Okay, so I'm going to write that shell model configuration. Okay, and there is a trick. I'm going to write that trick. Okay, this is important. You need to note down because many questions will be asked in the examination, and if you know the shell model configuration, then you will be able to solve those questions. Okay, so this is very important. So I'm going to tell you the trick how to remember or how to memorize the and how to learn that trick. Okay, how to learn this configuration. Okay, there is a trick, guys, very important. So I would request you, please pay attention carefully. Okay, so what we first will write SPDF. Okay, SPDF. So D will there would be, so D, between D there would be S. Okay, between F there would be P. Okay, first you need to know this. Okay, and then you can write GG, DD, SHH. At least you should know till this. Okay, if you know this is good, because right, but at least if you know this one SPDF and these D is S, D will split into S and F will split into 2P, and means that is enough. Okay, but I'm going to tell you the configuration for these as well. Okay, GG, DD, SHH. Okay, so how I'm going to write it here, right? First S means this is S half. Okay, so in S there would be 2 electron. Okay, and then S half. Okay, for S there would be 2 electron. P there would be 2 part of P. In P there are 2 means in P there are 2 levels. Okay, in total electron is 6. In P there are 2 levels. One is P 3/2. In this level there would be 4 electron, and then P 1/2. So for P there would be 2 level, P 3/2 and P 1/2. For S there would be only 1 level, that is S half. Okay, so this so total electron in P orbital is 6, right? So 4 here and 2 here. This you need to understand. For D, so D will start with D 5/2, higher than lower. Okay, 5/2, and in between D there would be S. So in D there are how many electron there are? There are 10 electron, right? So 6 electron will be in D 5 by 2. Okay, then in between D there is S. Okay, so S half, and in S half we know there are 2 electron. Then D, so D will be 5 by 2 and 3 by 2. D 3 by 2, and there would be 6 electron here, total 10, right? There would be 4 electron. Okay, next F. F will start with F 7 by 2. In F there are total 14 electron, right? So 8 electron will be here. Then then we'll write P 3 by 2. First higher value, then lower value. P 3 by 2, there would be 4 electron. And then F 5 by 2, there are 2 P, right? F 5 by 2. So there are this one. F 5 by, there are 6 electron. Okay, there are 6 electron. And then P, because there are P, right? So first F, P, F. P 3 by 2 means 1 by 2, and there would be 2 electron. At least if you know this till this configuration, right, you can solve all the questions, but it is good to know this as well. Okay, so understand this S half, there would be only 2 electron in S. Okay, P, there would be 2 orbital, P 3 by 2 and P 1 by 2. So in 3 by 2 there would be 4 electron, and 1 by 2 there would be 2 electron. Okay, 4 to the 6. If you talk about D, so there will be 2 orbital, that is D 5 by 2 and D 3 by 2. So in 5 by 2 there would be 6 electron, in 3 by 2 there would be 4 electron, total electron 10. S is half, that is over 2 electron. Okay, then F. Here you need to, so in between D there would be S, or here F, first F, then P, then F, then P. Okay, so so F, there would be 2 orbital, that is F 7 by 2 and F 5 by 2. So first F 7 by 2 will come, and then P 3 by 2 higher value, then F lower value, F 5 by 2, then P 1 by 2. If you know this configuration, you can easily solve all the questions, guys. But I would suggest you know this as well. So X star from GG, DD, S, HH, right? So GG means G, there are 2 orbital for G. So for P 3 by 2, D 5 by 2, F 7 by 2 means G 9 by 2, and there would be 18 electron, right? 18 means 10 electron will be here. Okay, again G 7 by 2, 9 by 2, 7 by 2. So there would be uh, uh, 8 electron, total 18 electron in G, right? So F by 2. Now D, we know D 5 by 2 and D 3 by 2, right? How many electrons are there? There is 6 and there are 4. Now S, we know S half 1 by 2, sorry, S half, and electron will be 2. Now H means G 9 by 2, this will start with 11 by 2. So H 11 by 2, and in H you need to understand, in G there are 80 electron, in H there are 22 electron, means 12 electron here, and this one 12 electron here, and here this is going to be H, and H 9 by 2, and there would be 10 electron. That's what you need to know, guys. So for P you need to know there are 2 value, P 3 by 2, P 1 by 2. For D 5 by 2, 3 by 2. For F 7 by 2, 5 by 2. For G 9 by 2, 7 by 2. For H 11 by 2 and 9 by 2. And electron and distribution of electron. For P 4 2, for D 6 4. For F, because the total electron are 18, right? So 14, that 8 6. For F there are 18 electron, so 8 6. This is F, there are 14 electron, 8 6. Okay, then if we talk about G, there are 18 electron, then 10 8. The ratio will be 10 8. And there are, for this, for D that's 6 4, and for H there are 22 electron, means 12 10. Okay, so this is the trick, guys. You need to know that SP, and then D will split into T. In between D there would be S, then F. First there are 2 value of, first F high value, then P high value, then F small value, then P small value, and then this is the This also you can note down. So this is very important trick, guys. Okay, I will solve one question, then it is going to be more clearer to you. Okay, so we have a question. So so you need to understand we have a question. Okay, so you need to understand this. So the JP, if it is JP is written, this means P is parity here. Okay, parity. J value. Okay, parity value is minus 1 to the power LP plus ln. What is LP ln? I'll tell you. We will find JP plus JN plus LP plus ln. Okay, if this value is even, okay, if this value is even, that implies value of J is going to be JP minus JN mod. Okay, JP minus JN mod. If this will be even, if suppose, then we have to find that total value of J. Okay, and if JP plus JN plus LP plus ln, this value is odd, this value is odd, in that case, this value is odd, in that case value of J is going to be JP plus JN. Okay, this is important one. Okay, now I will solve question, then this thing is going to be clear. Okay, question is, so we have 5 bismuth 10. Okay, and now we need to find out total value of J. Okay, this one, J value. Okay, we need to find J, this one. Okay, we have to find value of J. Okay, so how we are going to solve this? So here you can see for bismuth Bi, number of neutron and number of neutron is 5, number of proton is 5. So we'll make shell configuration. Okay, we're using this. So there are 5 electrons. So this is going to be for n equal to 5. The configuration is going to be s half 2 electron, and p 3 by 2. There are that only total 5 electron, right? 5 proton, right? For p. Okay, 5 proton, right? So this is going to be 5 means 3. Okay, so this one, so they would be 3. So total the configuration for p5 the proton p equal to 5, this is this p. So similarly for n equal to 5, the same configuration, because the number of neutron is same, right? S half to the power 2 and p 3 by 2 to the power 2, because total 5 electrons are there. So same configuration. Okay, so from here value of J for p, JP, value of JP, I'm writing directly. So value of JP is going to be this one, 3 by 2, and similarly value of Jn, this is also 3 by 2, right? This is the J value, 3 by 2, and value of LP means the P, value of P, L value, P is 1, right? And value of Ln, that is also 1, because this P means SPDF, right? SPDF, S0, P1, D2, F3, right? We know. So for Ln, this value is 1. So now we'll find this one, right? So parity is going to be, if you find parity, so minus 1 to the power L, we have to find JP. Okay, JP, we have to find parity is minus parity P is, I have already told you this, parity P is minus 1 to the power LP plus Ln, right? So minus 1 to the power LP is 1 plus 1. So this value is going to be, P is going to be 1, right? And now we'll find J value. So for J value we have to find this one. If this one, if the sum of this is even, then value of j is this. If sum of this is odd, then value of this. So we'll find that j value, right? So this is going to be j equal to we'll find jp plus this one. jp plus jn plus lp plus ln, right? jp value 3 by 2. Here you can see 3 by 2, 3 by 2, 1 1, right? 3 by 2 plus 3 by 2 plus 1 plus 1. So you can see the value is going to be 3 plus 5. This is odd. Odd means value of j is going to be this one, odd, right? Odd means value of it is odd, right? Odd means value of j is jp plus j, right? So value of j is going to be jp, means 3 by 2 plus 3 by 2, that is 3. Okay, this is value of j. So value of j is 3 and parity is 1. So jp is going to be 3 1 or 3 plus 1. Okay, like this. So this is how we find value and jp, or just we have to find j, then this is going to be 3. Value of j is 3. So this is how we use this configuration, guys, and many questions are asked in the examination. So you need to know this trick. This trick is very important, guys. Okay. So well, guys, I have completed the nuclear physics now. So in 2 lectures, I have completed the complete detailed course of nuclear physics. Okay. The first lecture was of 2 hours and 22 minutes, and this lecture is of almost 2 hours and 15 minutes lecture, guys. Okay. So in more than 4.30 hours, I have completed the nuclear physics, guys. So I would suggest you please watch my course, my nuclear physics course. Okay, all the detailed courses I have completed. Please check my playlist and watch it, guys. Okay, so this my courses are going to help you to crack the exams related to physical science, guys, especially CSIR, NET, GATE, NT exam, PhD exam, SET exam, TIFR, Just, IIT-Jam. Okay. Okay, guys. So also, guys, I would request the student who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures. And also, please share my lecture details to your friends so that they can also they will also be able to watch my free live lectures and they will also be benefited from it. Okay, guys, thank you so much. Bye now.